Hello everyone. Today I will discuss Cauchy sequences. This is one of the most fundamental concepts in real analysis. We know that convergence describes how a sequence approaches to a particular real number. Usually to check convergence, we need to know the limit in advance. However, in many situations, we may not know the limit beforehand, or the limit may not even lie inside the space. So we need a criteria that depends only on the terms of the sequence themselves, not on an external limit. That is why Cauchy sequences come into play. Cauchy sequences capture the idea that the sequence progresses, the terms become arbitrarily close to each other. This is the outline of my presentation. Now let us define Cauchy sequence. Let xn be a given sequence of real number. Then xn is said to be Cauchy sequence if for every epsilon greater than 0 there exists a natural number n1 such that mod of xn minus xm less than epsilon whenever nm greater than or equal to n1. This means that after some index, all terms of the sequence lie in a small cluster. They are pairwise close even if we do not know where they converge. Our first result is if xn is a convergent in R, then xn is a Cauchy sequence. That is, convergent implies Cauchy. Let xn be a convergent sequence and xn tends to L. To prove that xn is a Cauchy sequence, let epsilon greater than 0. Then for epsilon greater than 0, there exists a natural number n1 such that mod of xn minus L less than epsilon by 2 for all n greater than or equal to 1, since limit xn equal to L. And then for nm greater than or equal to n1, mod of xn minus xm less than or equal to mod of xn minus L plus mod of xm minus L less than epsilon by 2 plus epsilon by 2, that is less than epsilon. Therefore, xn is a Cauchy sequence. Our next result is every Cauchy sequence is bounded. Therefore, Cauchy implies bounded. Here we assume that xn be a Cauchy sequence. Choose epsilon is equal to 1. Then by definition of Cauchy sequence, there exists a natural number n1 such that mod of xn minus xm less than 1 for all nm greater than or equal to 1. Fix m is equal to n1. Then for all n greater than or equal to n1, mod of xn less than mod of x n minus 1 plus 1. Therefore, for all term with index greater than or equal to n1, mod of xn less than or equal to mod of x n1 plus 1. And the finite set is finite, and this finite set is bounded. Therefore, all terms are less than a fixed real number. Therefore, xn is bounded. Now, our main theorem is a sequence of real number converges if and only it is a Cauchy sequence. This is our main theorem. This theorem says that the convergence implies Cauchy and Cauchy implies convergence. In case of a sequence of real number, convergence implies Cauchy and Cauchy implies convergence. Therefore, it is a if and only theorem. One direction was already shown, that is convergent implies Cauchy. We will show here we will show that Cauchy sequence is convergent sequence. And to prove this, we will use Bolzano-Weierstrass theorem. Here xn is a Cauchy sequence, so it is a bounded sequence, and by Bolzano-Weierstrass theorem, every bounded sequence in R has a convergent subsequence, and thus there exists a subsequence xnk such that xnk tends to L. Using this fact, we will show that the whole sequence Xn converges to L. Here we will see that uh, the role of completeness has an important role. Now let us take an example. Let us consider the sequence 1 by n. Here we will show that 1 by n is a Cauchy sequence. To show 1 by n is a Cauchy sequence, let epsilon greater than 0. Now we can choose n1 with 1 by n1 less than epsilon, and such n1 can be chosen by Archimedean property. Then for nm greater than equal to n1, 1 by mod of 1 by n minus 1 by m less than equal to 1 by n plus 1 by m. This inequality is obvious, which is less than 2 by n1 and less than 2 epsilon. Thus, redefining constant gives the Cauchy property. And since limit 1 by n equal to 0, the result matches our previous concept. Now, if we consider the sequence sin n, we see that sequence sin n is bounded but not Cauchy. Actually, it is not a convergent sequence. Here you see that values do not cluster to a single point. They are dense in -1 to 1. And one can show that there exists epsilon greater than 0 such that infinitely many pairs nm have sin n minus sin m greater than epsilon. Mod of sin n minus sin m is greater than epsilon. So, it is not a Cauchy sequence. We can construct sequence of rational that approximate root 2, and it is Cauchy in Q, but has no limit in Q. This highlights that completeness matters, that is Q is not complete. These are the corollaries of our main results. That is, every Cauchy sequence is bounded. If a Cauchy sequence has a convergent subsequence, then the sequence converges to the same limit. And in a complete matrix space, Cauchy sequence implies convergent sequence, and convergent sequence is a Cauchy sequence. In numerical analysis, we check a sequence of approximation for Cauchiness to ensure convergence, because sometimes it is easy to show a sequence is Cauchy rather to show but its limit explicitly. In summary, Cauchy sequences capture the idea of internal convergence. In R, Cauchy sequences and convergent sequences are equivalent. Cauchy sequences are always bounded. Completeness is essential. In Q, some Cauchy sequences do not converge inside Q. Thank you. Thank you all.